Hi everybody, Mr. Bozade here. I am going to do the second problem here on worksheet 3, having to do with vertical circles, okay? So let's dive right in. The second problem says a 2.6 kilogram ball is tied to a string and then whirled around in a vertical circle at a constant speed of 16 meters per second. The string can withstand a maximum tension force of 130 newtons. What is the longest or shortest the string can be and not break? Okay, so remember, whenever we solve these problems, it's just like the second unit. We want to start by drawing our free body diagram and then writing our net force equation. So, but the one new thing, or one of the new things in this unit, is it's good to draw a dotted line tracing out the path of the object. So the ball and the string is going around in a vertical circle like that. Now, there's two key points that you probably would identify that you'd want to consider for this problem, right? You might want to consider what the forces look like on the ball there at the bottom of its swing and there at the top of its swing. So let's think through those real quick. At the bottom of its swing, force gravity points straight down and force tension points up, right? Like so. And at the top of the swing, force gravity still points down because that's not going to change, but force tension also points down. Now, here's the thing. We know that the net force has to point towards the center of the circle, right? So notice that in my bottom diagram here, I drew force tension larger than force gravity because the net force has to point towards the center because that's how the object turns around a circle if the net force points towards the center. In the top, however, both force gravity and force tension point towards the center. So in the top, the force, so together they form the net force that points radially inward. At the bottom, it's just force tension working against force gravity. The point I'm driving at here, in case you haven't figured it out, is that because of this, force tension has to be larger at the bottom than at the top because it alone is creating that net inward force. At the top, force tension and force gravity work together to form that net inward force. So why is that such a big deal? Well, because we want to figure out when tension force is greatest and equal to 130 newtons, so that is at the bottom of the swing. All right, so let's set up our problem, our net force equation for the bottom of the swing. So we got net force radially inward equals mv squared over r. Well, remember, anything pointing towards the center is positive, so that means that force tension is positive. Anything pointing away from the center is negative, so force gravity is going to be negative. So we're going to go plus force tension minus force gravity equals mv squared over r. All right, let's plug in some numbers. Let's see, force tension, 130 newtons is what we're looking for, or is the maximum force tension, so we'll plug in 130 newtons. Force gravity is going to be mg. The mass is 2.6 kilograms, so 2.6 kilograms times the gravitational field, which is 9.8, equals m, mass we just determined, we saw was 2.6 kilograms. Velocity, I think that is also given, a constant speed of 16 meters per second. So 16 squared over the radius. Okay, so now we just got to solve for that radius value. Let me start plugging these things into my calculator. Let's see, 2.6 times 9.8, that's 25.48. We'll subtract that from 130, and we get 104.52 equals... let's go ahead and multiply 2.6 times 16 squared, and that is 665.6 over the radius. All right, so what we'll do is we'll multiply the radius to the other side, and we will divide the 104.52 to the other side. All right, so then what we're left with is radius equals 665.6 over 104.52, and we discover that the radius is 104.52. Is 6, I was plugging that in my calculator, 6.3, let's say 6.4, we'll round it up. So the radius equals 6.4 meters. Now, we're not completely done because the question asks, so that is the perfect radius that will create a force tension of 130 newtons when the ball is swung at 16 meters per second. So the radius is 6.4 meters. So the question is, if the string gets shorter or longer, will the string snap? All right, let's see here. Well, because radius is in the denominator here, and force gravity is constant, right? It's 2.6 times 9.8. So force gravity is constant. If this side, if the right side gets bigger, then that means force tension has to also get bigger. Because right now, force tension minus force gravity, the combination of those two, is 104.52. So in order for force tension to get bigger, the right side has to get bigger. Now mass is constant, velocity is constant, so that means radius must be smaller. So if the radius is smaller than 6.4 meters, it's going to make the whole right-hand side of this equation get larger, which means the force tension would also have to get larger. So if the string gets any shorter than 6.4 meters, it's going to make tension get too big, and the string is going to snap because tension will become larger than 130. All right, that is everything. Good luck with the rest of this homework. See you Monday.